But can you truly imagine the power of a running dinosaur? But these fossilized footprints hold the secrets of their pace. And the spacing between these tracks is our first major clue. This is called pace, the distance between steps. But pace alone doesn't define top speed for a dinosaur. Skeletal morphology provides vital biomechanical constraints. The longer limbs generally allow for a longer stride length. A muscle mass dictates power output for acceleration. We use modern analogs, like birds or crocodiles, for comparison. The physics of force generation remains remarkably consistent across time. Now that we understand mechanics, let's explore specific trackway findings. Key paleontologists measure the trackway stride and print depth precisely. But these measurements feed directly into speed estimation models. The relationship between leg length and stride is crucial for calculations. Consider the apex predator, the Tyrannosaur lineage. Its massive legs suggest bursts of significant, though perhaps brief, velocity. However, sheer mass imposes physical limitations on running speed. Exaggerated strides might look fast, but strain the joints severely. Models often predict speed suggesting cautious pursuit, not Olympic sprints. Contrast this with smaller, lighter dinosaurs, the true sprinters. Their lower inertia allowed for rapid changes in direction and speed. Square-cube law influences everything about terrestrial locomotion at scale. The tail acted as a crucial counterbalance during high-speed turns. This stabilization mechanism is key to maintaining control while running. The narrow stance of many dinosaurs also maximized forward momentum. Air resistance, though less significant than modern jets, still played a role. A foot structure determined ground contact time and energy return. But now that we understand the evidence, let's explore modeling approaches. Engineers build robotic analogs to test hypotheses about muscle tension. Force plates capture the exact moment of ground contact and push off. Simulating substrate, hard ground versus soft mud, alters the results significantly. Inefficient animals minimize energy waste across their gait cycle. Metabolic rates and overheating also limit sustained high-speed locomotion. Every species presents a unique set of performance trade-offs. The ankle joint is critical. Too much extension risks structural failure. We must differentiate between sustained travel and short bursts of acceleration. For large predators, speed was a tool for ambush, not endurance. But large herbivores often moved at a steady, energy-saving pace. B. The geological record sometimes offers direct kinematic evidence of movement. The angle of foot placement subtly shifts as speed increases significantly. But even sensory input informed their speed calculations for hunting. Our superior vision compensates for slower reaction times in larger creatures. The evolution of feathered dinosaurs clearly favored high-speed maneuverability. The physics dictates that smaller animals are inherently faster runners. A microscopic analysis of bone histology provides fatigue limits. A true running involves a brief moment where all feet leave the ground. These biomechanical models generate speed estimates with probabilistic certainty. Ultimately, speed determines evolutionary success in the ancient food chain. But neural processing speed is another hidden factor influencing reaction time. And we return now to the broader context of their locomotion. An even slow movement by the largest dinosaurs was seismically impactful. Feathers, when present, offered aerodynamic benefits even at low speeds. All these disparate data points converge into a speed estimate. The best trackways provide a narrow, reliable window for interpretation. But we must accept that definitive top speed remains elusive by design. Their speeds were optimized for survival in their specific Mesozoic niches. But each new discovery refines our understanding of their ancient kinetics. The millions of years separate us from these incredible terrestrial athletes. The running dinosaur remains a powerful symbol of Earth's lost majesty. But their speeds are now calculated, understood, and forever etched in stone.